This video is brought to you by mywayteaching.com.
Now, next consider the problem. 13 gram of N2O4 was placed in a 1 liter reaction vessel at 400 Kelvin and allowed to attain equilibrium. That is N2O4. Okay, 2NO2. The total pressure at equilibrium was found to be 9.15 bar. Calculated Kc, Kp and partial pressure at equilibrium. Okay, what is they are asking? Kc and Kp. Solution. Note down the solution. We know that PV is equal to nRT. And next is total volume is equal to 1 liter. Correct. Molecular mass of N2O4 is equal to 92 gram. And number of moles is equal to 13.8 gram divided by 92 gram is equal to 0.15. Okay, 0.15. This is number of moles. Gas constant, that is R is equal to 0.0833 bar liter per mole per Kelvin. Temperature, that is T is equal to 400 Kelvin. And okay, and we know that PV is equal to N into RT. Now you know all the values and substitute in this equation 1. So what is P into volume is 1 liter is equal to 0.15 mole into 0.083 bar liter per mole per Kelvin into 400 Kelvin. And now you are getting P is equal to 4.98 bar into 4. Okay, and initial pressure that is 4.98 bar, and this will be 0 at equilibrium. 4.98 minus x bar to x bar. Hence, you are considering x. These are the steps which I have explained you. Hence, P total at equilibrium is equal to P par N2O4 plus PNO2. Okay, and P total pressure is equal to 9.15 and N2O4 is 4.98 minus x plus 2x. plus 2x, and you write 9.15 is equal to 4.98 plus x, and x is equal to 4.17 bar. Okay, partial pressures at equilibrium are partial pressures at equilibrium are P into 4 is equal to 4.98 minus 4.17 is equal to 0.81 bar. PnO2 is equal to 2x, that is 2 into 4.17, that is 8.34 bar. And now Kp equals PnO2 whole square divided by P into 4, 8.34 whole square divided by 0.81, 85.87, and Kp is equal to Kc into RT into delta N. 85.87 is equal to Kc into 0.083 into 400 whole raised to 1. So Kc you are getting 2.586 after the calculation, and you can simply write as 2.6. Kp value is 85.87 and Kc value is 2.6. Okay, next problem. 3 mole of PCl5 kept in 1 liter closed reaction vessel was allowed to attain the equilibrium at 380 Kelvin. Calculate the composition of the mixture at equilibrium. Kc is equal to 1.80. So consider this solution. PCl5, I am writing the balanced chemical equation. PCl3 plus Cl2. Now consider this initial concentration 3.000. Let x mole per liter of PCl5 be dissociated at equilibrium. So now you can write that as 3 minus x. This is x and this is x. Okay, and now Kc is equal to PCl3 into Cl2 divided by PCl5. Okay, and this is 1.8 PCl3, that is x square divided by 3 minus x, and now x square plus 1.8x minus 5.4 is equal to 0, and x is equal to minus 1.8 plus or minus square root of 1.8 whole square minus 4 minus 5.4. Okay, so divided by 2, and x is equal to minus 1.8. After this calculation of this plus or minus 4.98 divided by 2, and x is equal to minus 1.8 plus 4.98 divided by 2 is equal to 1.59, and PCl5 is equal to 3.0 minus x. equal to 3 minus 1.59. You are getting 1.41 mole, and then PCl3 is equal to Cl2 is equal to X is equal to 1.59 mole. Okay, next, relationship between K, Q and G, where K is the equilibrium constant, Q is the reaction quotient, and Gibbs energy is G. The value of Kc for a reaction does not depend on the rate of the reaction. However, it is directly related to the thermodynamics of the reaction, and in particular to the change in Gibbs energy, where change in Gibbs energy we can write change in Gibbs energy, that is we can write it as delta G. Delta G is negative, then the reaction is spontaneous and proceeds in the forward direction. If delta G is negative, so the reaction is first the reaction is spontaneous and forward react for and in the forward direction. Okay, and next, when the delta G is positive, the reaction is considered non-spontaneous. Okay, instead, as reverse reaction would have a negative delta G, the products of the forward reaction shall be converted to the reactant. So it is forward means here it is reverse direction. Okay, next, third one, when delta G is 0, the reaction has achieved equilibrium. So which is in equilibrium. At this point, there is no longer any free energy left to drive the reaction. Okay, so this is about delta G value. And now a mathematical expression of this thermodynamic view of equilibrium can be described by the following equation. So delta G is equal to plus RT ln Q. So where this is called standard Gibbs energy, okay, and now delta G is equal to standard Gibbs energy plus RT ln K is equal to 0, and this is equal to minus RT ln K. Ln K is equal to minus delta G standard Gibbs energy divided by RT. Taking antilog of both sides, we are taking antilog on both sides. So we are getting K is equal to e raised to minus delta G standard Gibbs energy divided by RT. Okay. Hence, using the equation K, the reaction spontaneity can be interpreted in terms of the delta G. Now, if Gibbs energy, standard Gibbs energy less than 0, then minus delta G RT, that is positive, and e raised to minus delta G RT greater than 1, making K greater than 1, which implies a spontaneous reaction or the reaction which proceeds in the forward direction to which an extent that the products are present predominantly. So we can say that it is a spontaneous reaction. Like if Gibbs energy is greater than standard Gibbs energy is greater than 0, and if this one is okay, this is negative, and this will be less than 1, making that is k is less than 1, so which implies this is a non-spontaneous yes reaction, or which proceeds in the forward direction to which small degree, and that only a very quantity of product is formed. Okay, this is the relationship between the equilibrium constant k, reaction quotient q, and Gibbs energy g.